In this video, I want to introduce the idea of a Hamilton graph, or sometimes called a Hamiltonian graph. So a Hamilton cycle in a graph is a cycle that uses every vertex. So it's one sometimes called a spanning cycle. It's one that's going to hit every single vertex in the graph. But unlike Eulerian graphs, right, now we're not talking about circuits. We're not allowed to repeat any vertices. We're talking about cycles, like we talked about in the very beginning of the class. So if a graph has a Hamilton cycle, then we call it Hamiltonian, or we call it just a Hamilton graph. And we have this similar idea of a path. A Hamilton path is a path that uses every vertex, right? So in neither of these are we allowed to repeat vertices. The difference is whether we start and end in different places in the path, or whether we begin and end at the same place in a cycle. So let's just sort of delve in and see if we can explore this a little bit. So find a Hamilton cycle or explain why one cannot exist. Okay, so we're going to do this a couple of times. So you may just want to pause the video and play around for a second and see if you can find a cycle in this graph that uses every vertex. So remember, Eulerian is edges, right? Euler starts with E, edges starts with E. Hamilton is vertices. So see if you can find a circuit that uses every vertex, or a cycle rather, that uses every vertex. Okay, there is one. So let's just list one over here. So it says to find one or explain why one can't exist. So we'll just find one. So let's say we start at vertex 1 and we go to vertex 4. Okay, so V1, V4, and then maybe we go to 2, V2, and then we go to 5, V5, and then we go to 3, V3, then we go to 6, V6, and now we've been to every vertex, right? 1, 4, 2, 5, 3, 6, and so then the question is, can we close the gap here? But we can, right? There's this edge from V6 to V1. So here's our example of a Hamiltonian cycle in this graph. Okay, so let's try this again, and let's look at this graph. Okay, so again, you may want to pause the video and just think about this for a minute, or try and play around with it and see if you can find one. The answer in this case is that there is not one. So we might want to think about why that is. In particular, if we want to visit every vertex, we want to have a cycle that uses every vertex. So you can imagine somehow like sort of walking around, like if you start at vertex number 1, maybe you walk to vertex 7 or you walk to vertex 2. And if you ever want to walk to, say, vertex 2, how can you do it? You can either go from 1 to 2 to 7, or from 7 to 2 to 1, right? Because this vertex only has degree 2, so that means that if you want to include this vertex, you have to use both this edge and this edge. Right? There's no way around it. There's no way for you to include vertex 2 without using these two xed edges. Okay, so thinking about that, how many vertices do we have like this in this graph? Well, there's vertex 2, which is degree 2. There's vertex 5, which is degree 2. And there's vertex 3, which is degree 2. Okay, so by our same rationale that we used a second ago, if we wanted to have a Hamiltonian cycle, right, if there were one in our graph, let's just see, I'm copying down all our vertices here. Okay, so for example, this represents V2, and we would have to use both those edges, right? Those are the edges that we just put the x's on. Similarly, if we want to visit V3, we're going to have to use both of these edges. Right? They're the only two going in and out of V3. And if we want to use V5, we have to use both of these edges. Okay, now all we've done here is say that if we have a cycle, they have to use these, right? This one, this one, this one, this one, this one, and this one, because all of those edges connect to degree 2 vertices. And so there's no way to include these vertices unless you include both of those edges. But now what's happened over here? Is there any way that you can just add edges to this and create a cycle? No, there isn't, because we've got a vertex of degree 3 already, right? But if you want a cycle, I mean, you can sort of imagine them looking something like this, right? A 6 cycle or a 4 cycle. And all the vertices in a graph like this are only going to have degree 2, right? Every vertex has exactly degree 2 in a cycle. So this is never going to have a cycle. Okay, so there, let me write a quick justification here. It's impossible to have a Hamilton cycle and then I gave the sort of justification here already, so just as a reminder for what we were talking about, I'll just say consider the degree 2 vertices, or consider the edges incident with degree 2 vertices. So if you were doing this in a homework or something, you would have to sort of give me better justification than just what I've written here, and it would involve drawing this picture here and explaining, right, that when you get this degree 3 vertex using only required edges, right, the only edges we've included over here were required ones, then now you've sort of guaranteed that you can't have a cycle. So this is our brief introduction to Hamilton cycles, and there's going to be a part 2 where we talk a little bit about how you can determine when a graph does or does not have a Hamilton cycle, other than just finding one, like we did here in the purple graph. So that's the end of this video.